Hello. Today we're going to start looking at graphing complex rational functions. Now don't feel intimidated by this wall of text that you see in front of you. I'm going to talk through it too, so we can kind of think about it together. Okay, so first of all, let's consider our function here, 1 over x minus 2 plus 3. Okay, this is a simple rational function example. How can we tell it's simple? Well, I mean, it's a very clear transformation of our parent function 1 over x, right? We can see we're shifting right 2 and up 3. So nothing too crazy there, right? Okay, one piece of information that we know about this, right, that we were kind of like talking about even before graphing these things, is you know that x can't be 2. And the reason for that is because f of x has a vertical asymptote at x equals 2, right? And so those things are connected. And why can't x be 2? Why does f have this vertical asymptote? Okay, well, what's the reason there is because f of x approaches infinity as x approaches 2 from the right. Okay, so our function approaches positive infinity as we approach 2 from values that are bigger than 2, like, 3 point, or like 2.1, 2.01, 2.001, stuff like that, right? Okay, the function value just increases as we get closer and closer to that 2, because we're going to do 1 divided by a very small number there, which makes that number very big. Okay, and so that causes our function to not exist, okay, to be undefined. Same thing happens too if we try and approach 2 from the left, okay, from values that are smaller than 2, so like 1.9, 1.99, 1.999. The closer we get to that 2 from the left-hand side of 2, we're going to subtract 2 from those numbers, and that'll be a very, very small negative number, very, very close to 0. 1 divided by that number is going to then, again, make it big. And again, this is something we kind of investigated, I think, yesterday with, or the day before with a table and stuff like that too. And you can kind of look at it with a table too. But we're going to talk about some other functions here too. So we could look, for example, at this function right here, okay? Where will it have a vertical asymptote? Well, we can very clearly see here that x minus 1 is going to, be a possible way for us to equal 0. So if x equals 1, that's a vertical asymptote, right? Because at 1, this would make our whole function become something over 0. In fact, very specifically, it would be, 4 over 0. And of course, divided by 0, undefined, goes to infinity and stuff like that, or negative infinity, depending on the side. Okay, for this function right here, what x values would cause us problems? Well, it's going to be x equals negative 1 and x equals 1. Okay, and we would say both of those are vertical asymptotes. Okay, and this one I'll go ahead and graph for us. So you can also see here, this is an example of a complex function that we will be graphing because it's got 2 vertical asymptotes. Oops, sorry. So if I then go to my graphing calculator here, I already have this first example ready for us to graph. So I'll show you what it looks like here, and we're going to be able to come up with a graph for this. So you can see there's our first vertical asymptote and the other one, okay? So I don't know if you guys will be able to see my pen right in here, but you can kind of see, okay, there's, both of our vertical asymptotes. We get this kind of funky graph. And again, don't fret too much. We'll go over about how to do this, not today. Today I just want to focus on these asymptotes and the different kind of behaviors we can see, okay? So then let's talk about this last function right here, okay? So this one, it's kind of hard to see what's going to make us divide by 0 potentially here because we need to really factor that denominator. So we're going to factor the denominator here. It does factor. So it's going to be x minus 3 and x plus 2. Ooh. Like so. Right? Okay, so you might look at that and say, okay, so a 3 will make us 0 here, and a negative 2 will make us 0 here, so x equals 3. Actually, let me do it in order. X equals negative 2 and x equals 3 are going to be vertical asymptotes, right? And so let's check our graph. Okay, so I'll go back to my graphing calculator here, and I have the other function here ready to show you. And there's our vertical asymptote at negative 2, but at 3, at x equals 3, you'll see there's no vertical asymptote. It looks like the function just kind of like continues on as usual there. No asymptote. So what is happening? So we did get the vertical asymptote at negative 2. That's true. But then this, what is that? Well, let's investigate a little bit. So let's investigate what happens. Ooh, I didn't spell happens there, right? What happens to this function as we approach that 3? Okay, so again, we're going to use the table on our graphing calculator here. I'll approach 3 from values that are less than 3, that means from the left, and I'll approach 3 from values that are greater than 3, that means from the right. Okay, so let's fill in these tables here. So I'll go back to my graphing calculator. Okay, I already have it, graphed here, so I'll go to my table. All right, and let's get, again, we're going to approach from the left, so I'll do like 2.9, that's pretty close to 3, and then 2.99, and then 2.999. And wow, you can see here that our graphing calculator, the y values here are not getting, they're not going to infinity like for our vertical asymptotes, but they do seem to be getting closer and closer to a particular number. Okay, in fact, our calculator goes ahead and just rounds that last one to 1.8, even though you can see the decimal down at the bottom there of the screen is 7.999599992. Okay, but they go ahead and just say it's 1.8. And in fact, if you get even closer, doing like 2.99999 like that, you can see it still goes to the 1.8, and now it's even closer. Look at how close it is to 1.8. Okay, so going back to this then, oof, well, you get the idea. Something like that, basically. So we're getting very close to this number 1.8. Well, let's see what happens as we approach 3 from values above 3. So we'll do, again, I'll delete these out. So we'll do 3.1. That's above 3, but pretty close. 3.01, now we're even closer to 3. 3.001, now we're even closer to 3. And hey, look at that. We get super close again to that 1.8. So, I don't know, something. And then it just says 1.8. Okay? So, for our asymptotes that we had, when we do the table with those, we end up with our values approaching either positive infinity or negative infinity, and that indicates an asymptote. This, however, we end up with a value that we're approaching, a number. So as x approaches 3 from below or above, right, because in both cases, f of x was approaching what value? Well, it looks like it's approaching 1.8. But at 3, there's no pointer value, right? If I go back to my table here, and if I type in 3 exactly, you see I get an error. So we can get very close to 3, but at 3 there is no point or value. What do you call, but we have this location though, we approach this 1.8. So we have this location, 3, 1.8, right? As we approach 3 from above or as we approach 3 from below, both cases we're getting closer and closer to 3. But at 3 there is no point. So how do we indicate something that doesn't exist? We're going to put a hole, a single open circle like that in our graph, and that will indicate a single non-point. Okay, so we can get as close as we want to 3, and the closer you get to 3, the closer we're going to get to 1.8 on either side in this particular function. But if we get to 3, if we actually get at 3, there will be a hole, an open circle, indicating a single non-point. How can we see this then? Do we have to go through this whole table mess every single time we run across a situation? Well, no. Let's examine the difference here between what's happening at that 3, where we got the hole, and what's happening at that -2, where we got the vertical asymptote. Okay, so if you take our original function here, and you factor that numerator in addition to factoring the denominator, you'll see something interesting. What you notice is in common to both the numerator and denominator. So they both have this x minus 3. And so if we can imagine canceling those out, you'll see that that x plus 2 still remains. And so that indicates to us, right, that at x equals -2, there's a vertical asymptote because it's non-removable. Okay, you can't get rid of it. This x minus 3, though, we can get rid of it in quotes, okay, because it's it can cancel out. Remember, that still doesn't allow us to we still have to exclude those x values, though, but it's a different kind of discontinuity. It's a hole, and we call that a removable because you can kind of get rid of it, right? You can cancel it out in some sense. But both of these are examples of discontinuous, okay? Because the function breaks up. At that point, it's not nice and smooth and continuous. It breaks up. The vertical asymptote is a much different kind of discontinuity than a hole, right? But they're both discontinuities, all right? So that's how we're going to indicate whether we have a hole or a vertical asymptote. So let's take a look here at these, all right? If we look at this function as an example, all right, we have clearly only one x value here that's going to cause a problem, and that would be at x equals 2. Okay, now, can we cancel out that x minus 2 with the x plus 1? The answer is no, right? It doesn't cancel out. So this is going to be a vertical asymptote for sure. Okay, you can verify that on your graphing calculators too. If we go to our graphing calculators, okay, and I type in, when you type these rational functions in, please make sure you put parentheses around your numerator and parentheses around your denominator. X plus 1, close parentheses, divided by x plus 2. No, x minus 2. Okay, and we'll go to our table, and we can see here that as we approach 2, if I approach 2 from values below 2, so like 1.9, 1.99, 1.999, you can see that our, when I need to turn off this other function, sorry. There we go. Okay. So as you can see here, as we approach, we're getting bigger and bigger and bigger, right? Very, very negative. If I approach 2 from values above 2, 2.1, 2.01, 2.001, you can see here that now we're getting really big values, okay? You're going to infinity. So one side goes to negative infinity, one side goes to positive infinity. That indicates a vertical asymptote, right? And so we have the vertical asymptote too. What about this function? Well, at first glance, you might think to yourself, oh, x equals negative 3 is going to be a problem, and that's a vertical asymptote. But let's check it up here. This thing factors. Oh, I didn't want to do this one. I wanted to put that actually, let me do this. Let me change this one. I don't like this one. Should have worked before. Let's do this one. There we go. Okay, I like this one more. So again, at first glance, let's take a look and factor this thing here. So x plus 1 over x minus 4, x plus 4. Well, that's frustrating. Why would they do that to me? All right, here's what I'm going to do. Change this up. Voila. Okay, there we go. That's the problem. So, again, looking here, we're like, okay, x equals negative 4 is going to make us divide by 0. X equals 1 is going to make us divide by 0. But there are two different kinds. This x equals negative 4 is going to be a vertical asymptote. How can we tell? Because it won't cancel with anything from the numerator and denominator, right? However, the x minus 1s can cancel, so that indicates there's going to be a hole here. And if you graph this function, you'll see that vertical asymptote at x equals negative 4, and you won't see the hole at 1 because the graphing calculator doesn't quite have the resolution to do that, okay? But what we can do is still use this canceling out here to help us figure out what the y value for that hole will be. If we now plug 1 into this function, okay, we'll be able to see what the y value for the hole will be. So 1 over 1 plus 4 is 1/5. And so the hole is actually at the point 1, 1/5. And then the vertical asymptote will be there. Okay, so I'm going to give you guys 2 problems to try for homework that will result in, just to identify vertical asymptotes or holes. Tomorrow we will learn about how to find horizontal asymptotes and then put that all together to graph